Namaste everyone. Welcome to the second PUC physics class, and now we are in the fifth problem. We are solving alternating current chapter problems. So here is the fifth problem. Namaste, welcome to the class. We are in the second video of the problems. A series LCR circuit with R equal to 20 ohm and L equal to 1.5 Henry and C equal to so much is connected to a variable frequency 200 volt AC supply. Frequency is not given. And when the frequency of the supply is equal to the natural frequency of the circuit, okay, when they are equal, what is the average power transferred to the circuit in one complete cycle? Yes, what is power dissipated? You know that it is VRMS into IRMS into cos phi. But when the natural frequency, that is 1 by 2 pi root LC, and applied frequency are same, the circuit is at resonance. Now it is purely resistive because inductive and capacitive reactances cancel each other. XL minus XC becomes 0. Net reactance becomes 0. So root of R square, Z equal root of R square, Z equal R. So it is purely resistive. So cos phi is 1. VRMS into IRMS is enough for us. Power is equal to VRMS into IRMS. Power is equal to VRMS into IRMS into this cos phi. At resonance, cos phi is equal to 1 because it is purely resistive, because phi is 0, circuit is purely resistive. So power dissipated at resonance is VRMS into IRMS, right? That's all. So how to find out that VRMS and IRMS? VRMS is given, isn't it? 200 volt. When the frequency of the supply is equal to natural frequency, yes. Now you have to find out what is IRMS. So VRMS is given. It is 200 volt. Where is that? 200 volt. This one itself. What is IRMS? IRMS at resonance is very easy. IRMS at resonance is V by R because Z equal to R at resonance. So V by R. VRMS is 200. Of course, I don't write sometimes RMS because everything is understood. It is RMS. 200 by R. R is 20. So this is 10 ampere. So what is power dissipated? Power is equal to VRMS, that is 200, and IRMS at resonance, that is 10. It is 2000 watt. Is it the answer? Yes, 2000 watt. Very simple problem. Right? Once you know the theory, you see, now you can understand what is the importance of the theory while solving the problem. If you don't know the theory, impossible. You must know all these things. Simply the values of inductance, capacitance, etc. are given, and you have not been asked even to find out the resonant frequency. It is not needed for finding out the power factor or power. So unnecessary values are here, so it may confuse you if you don't know the theory. So 2000 watt. Next one, sixth. A radio can tune over the frequency range of a portion of megawatt broadcast band. That means 800 kilohertz to 1200 kilohertz. So radio has to work between these two frequencies, 800 kilohertz to 1200 kilohertz. That means that radio station is not exactly picking up one frequency. Somewhere between 800 and 1200 kilohertz, it should have a natural frequency. So even for 800 hertz, its current is not very low. It is somewhere around 1 by root 2 of the maximum value, even for 1200 hertz also. So it is working in a range. If its LC circuit has an effective inductance of 200 microhenry, what must be the range of its variable capacitor? You know, I have told how do we radio. This is not radio station. Sorry, this is a radio which can tune over the frequency of range. That means, yes. A radio should be able to receive 1 by 1 frequencies. If you want to receive 800 hertz, 800 kilohertz, of course, it is 800 kilohertz. If you want to receive 800 kilohertz, yes, you must tune it. If you want to receive 1200 kilohertz, it must receive. You have to change it as your requirement, right? 1 by 1. Sir, what we will change? Inside the radio there is a resonance circuit, we know it. And there is a series resonance circuit, R, L and C. Okay, this is not needed for this problem, right? So inside the radio there is a series resonance circuit, and so R, C and L. If you can, if you want me to remind the things. And here is not AC, and here is the antenna. Antenna feeds those AC signals. all the signals from the transmitting station from Bangalore, Mysore, Bangalore, Hassan, every radio station program, Belgaum, everything will come and hit the radio antenna. Antenna will receive it, but circuit won't receive all the things. It will receive only one frequency for which this is 1 by 2 pi root LC holds good. L, C and R. For which resonant frequency, for which, suppose you calculate this L and C and substitute here and get the value of resonant frequency as, say it is 1000 kilohertz, then that 1000 kilohertz range frequency is received. Other frequencies are rejected because it is not the resonant frequency of that circuit. Current will be less. It is a highly selective circuit. And now, of course, it is not a radio station, it is a radio receiver. Okay, that in the beginning I misunderstood it. It's a radio receiver. Receiver should receive only one frequency. Transmitting stations, one by one, different stations will transmit different frequency, electromagnetic waves. Okay, now this is the frequency which it will receive. Sir, I want to receive 1200 kilohertz. What I can do? Change the value of C. That is what we do in radio. We just tune it, right? When you tune it, the capacitance changes, distance between the capacitor changes, and the capacitance value changes because C is equal to epsilon naught A by D. It is inversely proportional to the distance between the capacitor plates. Capacitance is inversely proportional to the distance between the capacitor plates. So, what happens? When distance changes, when you tune it, capacitance changes, resonant frequency changes, so you change it, and you can receive another station. So by changing the value of C, you can change the frequency which is received. But all the times, all the signals will be entering the radio. When we are receiving Bangalore station, don't be under the impression that Mysore station signals are not received by the radio. Of course, radio receives it, but it rejects it. Why? Because inside resonance circuit is not working for that frequency. It doesn't give highest current for that frequency. If you want Mysore station to be received, set the capacitance value in such a way that when you substitute here, you get the resonant frequency of that electromagnetic wave sent by Mysore. That's what you have to do. So now, what else? So this radio has to work between 800 kilohertz and 1200 kilohertz. From where to where you have to change the capacitance? That is their question. That means inside the resonance circuit, capacitance must be varied from certain value of C such that you can receive 800 kilohertz to another value of C which can receive 1200 kilohertz. To such an extent, the capacitance has to be changed. What is the value of capacitance has to be changed? We don't change the value of inductance. We keep the inductance value constant because inductance value cannot be changed so easily. Okay, that's what it is given. Hint, for tuning the natural frequency, that is the frequency of the free oscillations of the LC circuit should be equal to the frequency of the radio wave. Yes, that explanation I have given. That LC should be selected in such a way that 1 by 2 pi root LC, what the frequency we get, that should be the frequency of the wave that we want to receive. Okay, so what you have to do is, for receiving 800 kilohertz, right, L value is given, what should be the C value? That is one C value. Calculate another C value for 1200 kilohertz. That's the range of frequency that you have, the range of capacitance that has to work inside. Okay, you know that resonant frequency is equal to 1 by 2 pi root LC, right? And if you square this, what you will get? Because I want to put it for C. If you square this, nu naught square is equal to 1 by 4 pi square LC. What is C? That implies C is equal to 1 by 4 pi square nu naught square C. L. Right? 1 by 4 pi square nu naught square L. Now C1, 1 by 4 pi square nu naught square. What is nu naught? That is 800 kilohertz. Yeah, we want to receive 800 kilohertz. Nu naught square, right? Nu naught square. L is same, that is 200 microhenry. 200 microhenry. No square for L because it was inside the square root. Let me use a chalk. Yeah. C1 is equal to, oh, this is a big one, 4. 3.14 square. Then, shall I take two zeros and write separately? 64 into, this is 10 to the power 5, right? 800 into 10 to the power 3. This is 100, this is 1000, 10 to the power 5. 10 to the power 5 whole square is 10 to the power 10. Hope you have followed. 8 square 64, 100 square 10 to the power 100 10 to the power 2, 5 square 10 into, then 4 pi squared nu naught squared c, sorry L is here 2 into 10 to the power minus 4. These two zeros plus 2 minus 6 minus 4. So what is this? C1 is equal to totally this is 10 to the power 6 here, this one and this one 10 to the power 6. When I bring it here 10 to the power minus 6, then I will calculate. Yes. Then 1 by 4, 1 divided by 4, I know what is 1 by 4, that is 0.25. Yes, divided by 3.14, again divided by 3.14 equal to, divided by 64 equal to, divided by 2 equal to. So this is point, you're not getting answer. Yeah, here it is picofarad to picofarad 10 to the minus 12. Okay, let it be 0.000. The answer is like this, 0.000. Where is the point, decimal point? I can't see the decimal point at all. Okay. 1980. Here is the decimal point. 0.000 1980. Enough. Are you getting that answer? Yeah. Okay. Minus 6. I will take one more. 1, 2, 3, 4, 5, 6. 198.0 into 10 to the power minus 6. That is this one. This much into 10 to the power minus 6. This one. That is equal to 198.0, 10 to the power minus 12 farad capacitance, that is 1980 or 8.0 picofarad. That is one answer. 0.1 they have written, of course that is a 0.09 we have got. Next one, C2. C2 is equal to, I think you can see it here, C2 is equal to 1 by, only this one is changed. Instead of 800 we have 1200 kilohertz. 4 pi square, okay, f square nu naught square 1200 into 10 to the power 3 whole square, and C is 200 micro. Okay, what else? C2 is equal to 1 by 4 pi square. So this is 12. 12 is 144 square. 10 to the power 10 once again. 2, 3, 5. Then this is 2 into 10 to the power minus 4 as it is. What is C2? C2 is equal to 1 by 4 into 3.14 square into 144 into 10 to the into 2 one more into 10 to the power minus 6 plus 6. C2 is equal to 10 to the power minus 6. And what else? 1 divided by 4, that is 0.25, divided by 3.14 equal to, divided by 3.14 equal to, divided by 144 equal to, divided by 2 equal to. Okay, 1, 2, 3, 0.0000880. Minus 6, one more minus 6, C2 is equal to 1, 2, 3, 4, 5, 6, 88.0 into 10 to the power minus 6, that is this one, into 10 to the power minus 6, this one. C2 is equal to 88.0, 10 to the power minus 12 farad. Picofarad. Pico is 10 to the minus 12. Do you have? Yes, 88.04 picofarad. So that is another answer. Okay, shall we move on? Yes. 7th problem. A coil has an inductance of 0.2 Henry. In the previous problem, one thing I would, so your capacitor must have, that the plates of the capacitor must be they should be moving from one region to another region. That means they should move through a distance such that the capacitance should vary from 88 picofarad to 198 picofarad. So when it is 88 picofarad, you will get 1200 kilohertz resonant frequency. it will be received. When it is 198 picofarad, you must be able to receive that 800 kilohertz resonant frequency. So in between, when the capacitance is somewhat like 100 picofarad, 120 picofarad, 150 picofarad, you will receive different frequencies between this range. So that radio can be used to receive different frequencies. That is the meaning of the problem. Okay, 7th one. A coil has an inductance of 0.2 Henry and a resistance of 40 ohm. It is connected to an AC source of 220 volt 50 Hz. Calculate the power dissipated in the circuit. So it is neither in resonance, it is not in resonance, it is somewhere else. So we will have to think of what is the frequency and all. Yeah. Power dissipated is Vrms into Irms into cos phi. Correct? If it is Vrms into Irms into cos phi, you need to find out Vrms, Irms, even cos phi, because it is not at resonance. So we will calculate 0.2 Henry and 40 ohm, only two components. So components are capacitor is connected. Okay, shall I divide this? If needed, I will use the other part of the board. Now for the timing, I'll write only here. Okay, right. Yes, L 0.2 Henry. Then R 40 ohm. Chalk pieces. Okay. Then AC source 220 volt and 50 hertz. Nu naught. Nu is 50 hertz. Don't know it is resonant frequency or not. Calculate the power dissipated in the circuit. Okay. XL we have to find out. 2 pi nu L at that frequency may not be at resonance because there is no capacitor at all. Then how can it be resonant circuit? 2 pi nu L, 2 into 3.14 into 50. So L 0.2. This is 314, right? Because 2 into 50 is 100, 314. 314 into 0.2, that is equal to 628, 62.8 ohm. If it is into 2, it should have been 628, but 0.2, 62.8 ohm. L is okay. Then Z is equal to root of R squared plus XL square only. Root of XC minus XL whole square, only XL square. Z is equal to root of R square, 40 square, am I right? Is it? Yeah, 40 square plus 62.8 whole square. Z is equal to, you have to find it out, 40 square, 62.8 you will do first, 62.8 into 62.8, that is plus, because we know 40 square, 1600, 40 into 40. Right? Yeah, 1600, that is equal to square root. Yes, 74.46. 74.46. 456, but I'll approximate it to 46 ohm. Okay, that's over. 1600 plus 62.8. Okay. Next, Z. I we have to calculate. Calculate the power dissipated in the circuit because we want I. Vrms into Irms into cos phi. That's what we need. Irms Vrms divided by Z. That is equal to Vrms. It is 220 divided by Z, 74.46. That is equal to 220 divided by 74.46. Yes, is equal to 2.955. I can write 2.9546 5 ampere. So what is power dissipated? Power is equal to, it is you need cos phi is equal to, right? What is cos phi? Cos phi is equal to R by Z. That is equal to R is 40 ohm, am I right? 40 ohm divided by Z. Z is 74.46. So let it be like this. We will substitute it. Vrms, Irms into cos phi. That is equal to Vrms 220, IRMS 2.955, cos phi 40 divided by 74.46. Because separately they have not asked you to find out power factor, so you need not worry. 220 into 2.955 into 40 is equal to divided by 74.46, 74.46, that is 349.23, yes, 349.23 watt. This is the power dissipated. Okay, that's one type of circuit where we don't have capacitor, we have only inductor. But formulas go as it is. Whatever is not found in the circuit, just leave it. 8. A 1000 ohm resistance and a 0.5 Henry inductance are connected in series. Okay, inductance and resistance into an AC source of 110 volt 50 Hz. Calculate the current flowing in the circuit, power factor, phase difference between voltage and current. Very similar problem, right? But you have different things to be calculated, that's all. Okay, we'll move on. Right. Yes, a 1000 ohm resistance R, 1000 ohm, a 0.5 Henry inductance L, 0.5 Henry, and are connected in series to an AC source of 120 volt, 110 volt, 50 Hz AC. Okay, calculate the current flowing in the circuit. So phase difference, power factor. Okay, however you have to calculate Z, there is no other way. I is equal to V by Z. So what is XL? XL is equal to 2 pi nu L. Shall I write directly? 2 pi nu. Okay, I'll substitute now. Next time I will write, if it is 50 Hz, I'll directly write 314. 2 pi nu L. L is 0.5 Henry. That means half. That is equal to 314 into 0.5. 0.5 means half. Half of 314. It is 157 ohm. Half of 314 is 157. 150, 150, 300. 7, 7, 14. Okay. Now, what is Z? Z equal to root of R square plus XL minus XC whole square, or XC minus XL whole square. It is XL square root of R square 1000 square plus 157. Is it 1000? Yeah. 157 square. That is equal to Z is equal to root of 1000 is 10 to the power 6, right? 157 into 157 is equal to this much. This is 10 to the power 3 square, 10 to the power 6. So plus 1, 2, 3, 4, 5, 6, 6 zeros. So square root. The answer is 1012.249. Okay, directly answer. 1012.25 I'll write. Oh. Current flowing in the circuit, I RMS. I don't write RMS. I is equal to V by Z. RMS voltage V is 110. Z is 1012.25. 110 divided by 1012.25 is equal to 0.1086. Yes, exactly. 0.1086 amperes. This is the current. Then power factor cos phi equal to R by Z. R is 1000 by Z is 1012.25. 1000 divided by 1012.25. 0.987. No in it. 0.9878. So 0.988. Okay. Then phase difference between current and voltage. Okay, here only you can get phi is equal to 0.9878. It is 0.987898. So 79. I'll write same answer. Phi is equal to cos inverse of 0.9879. That is equal to, okay, cos inverse of 0.9879. I need not use tan phi formula because This is very useful both for power factor as well as phase difference. 0.9879. I would search for that number. 0.9879. My eyes will support me, I think. Such small numbers I would search. 0.9879. 0.9871 I have got. 7477 I have, and 0.9880 I have. That is 9 degree. 0.9 degree. 9.9 degree. 9 degree 4 minutes. Okay, 9.9 degree I have. It's 54 minutes actually, not 04. 0.9979. 0.99. Yeah, 0.9980 I have, or 0.99. Oh, it is 0.98. Sorry, 9879. Correct. 0.9879 means I have 77. So 9 degree, almost 9 degree. 9 degree 4 minutes they have written. It is enough. 9 degree. So phi is almost 9 degrees. You get it? That is enough. 4 minutes is not needed. Okay. So that is the phase difference. Very easy. Now I think you have got the grip of the problems. What to do? 9th one. Okay. It should be 9th problem. What about the next one? 10th. Yeah. 9th one. A capacitor and a 50 watt 100 volt electric lamp are this is a very important problem, very important type of problem. Here you will have to discuss the things. You will have a series of these types of problems now. Right. It's 9th one actually, not 0. 9th one. Yeah. A capacitor and a 50 watt 100 volt electric lamp are connected in series to a 50 hertz 220 volt AC source. Okay, I'll show it like this. I think we may in need of the space here. A capacitor and a 50 watt 100 volt source. 50 watt, it's a lamp, right? What about AC? 50 hertz 220 volt. 50 hertz 220 volt source is connected to a capacitor and a bulb. Like this, to an AC source. Capacitor is how much? A capacitor and a 50 watt 100 volt bulb. 50 watt 100 volt bulb. It is a specification of the bulb. You remember, try to remember what we have studied in current electricity. So it holds good. 50 watt 100 volt bulb is connected to 50 hertz 220 volt source along with the capacitor. Find the capacitance of the capacitor required for the lamp to glow. Okay, what is C? Question is, what is the capacitance of the capacitor to be connected, required to the lamp to glow? Does the lamp continue to glow if the capacitance of the capacitor is double? Justify your answer. Okay. If the capacitance of the capacitor is double, does the bulb continue to glow? Yes. What about the first one? What is the capacitance of the capacitor required? Now, why do you require a capacitor, first of all? What is the necessity of connecting a capacitance here? Very simple. You see, this is 220 volt supply. What about this one? 100 volt. What is this 220? RMS. Not mentioned. It is RMS. If this is RMS, this is also RMS, right? Not mentioned, RMS. That means this battery, this bulb can hold an RMS voltage of 100 volt. But we are supplying an RMS voltage of 220 volt. Will the bulb be able to hold it? Never. Bulb will never work with 220 volt. Its coil will get heated to a value, or the heat generated will be more than the required value. Bulb will burn off. Only the filament will be burnt. So what we will do? When we supply 220 volt, let us take care that only 100 volt appears across the bulb. How to do so? By taking another component, either capacitor or inductor or resistor, whatever it is. Take another component so that a part of 220 volt appears across this here. This is what do we do in DC circuits. Here also you can do that, but some items of DC circuits cannot be applied here. Suppose it is a DC circuit, say DC circuit of 220 volt. No frequency, 0 hertz. Why? A DC doesn't vary with time. It always flows with the same direction. How many times it changes the direction per second? 0 times. Frequency of DC is 0. So it flows in only one direction. Now suppose if I have a capacitor here and a bulb here. This is 220 and bulb has to be operated at 100 volt, correct? If bulb has to be operated at 100 volt, remaining 120 volts should be here. When? If it is DC, this is okay. Because in a DC circuit, there is no phase difference between current and voltage since it doesn't change the direction. In AC circuit, alternating current changes the direction. So there is a phase difference between current and voltage. As soon as this is 100, you can't say that this is 110 or 120. Because you know that phasor diagram, remember that phasor diagram. When the current through the resistor is highest, voltage across the resistor is also highest. But at that time, voltage across the capacitor will be lagging, current will be leading, right? How can you add these voltages? Can you add? So can I say, if I write here 120 plus 100 is equal to 220? No, you can't say. Voltage supplied is equal to root of VR square plus VC minus VL whole square. Here no L, VC square. If this is the resultant voltage, it is not simply VR plus VC. So we can't write 220 volt is equal to this 100 plus 120. That is possible only in DC. Here it is correct. Here it is not correct. We have to use this formula and find out what voltage this capacitor has to consume so that bulb will never get a voltage more than 100 and bulb is safe. So extra voltage which is other than safety of the bulb should be consumed by the capacitor. Such a capacitor we have to select. That is the question. What is the capacitance of the capacitor required for the lamp to glow, to bulb to glow, right? Is it focused properly? I don't know why it has changed. Yeah. Find the capacitance of the capacitor of the lamp to glow properly. Does the lamp continue to glow? If that is the second part. Okay. So you can't add. One point you have to remember, these voltages cannot be added. If they were in the same phasor direction, of course you could have added. So now, how to solve this now? Of course, you have to go for the AC method. That's all. Right. My calculator. Let them be here. They are filled with the chalk powder. Okay. Now, I don't know what is the voltage here. I don't know the capacity. Now, you just one thing you can seek the help of current. That's what we did in derivation, right? For Z, right? In phasor diagram, you can get the help of current because current flowing through all the components are same. That means find out what is the highest current that can be passed through the bulb. Then that current should be the current through the capacitor. That is our the way of solving the problem. So find out the current in the circuit. There is no discrimination for current. Current flowing through all the components are same. They are in phase. So what I can do, find out for bulb I will write. Now I am applying only for bulb. Power is 50 watt. And voltage is 100, right? What is current? If it can tolerate a maximum power of 50 watt, then what is the highest resistance of the bulb? I can treat this as a resistor. And what is the current? Power is equal to Vrms into Irms into cos phi. This is 1 for a bulb because bulb can be treated as a resistor. Because what does bulb contain? Only a tungsten filament inside, right? Tungsten filament is only resistance. It will not have capacitive effect. It will not have inductive effect. It is simply a coil. It is simply a resistor. It is a tungsten wire. So if it is a tungsten wire, then why can't you use this formula? Cos phi is 1 because it is a resistor. So what is power? Power is 50. Voltage is 100. What is Irms? So Irms current that can be possible for the bulb is 50 by 100, that is 0.5 amperes. This is the maximum current that you can pass through the bulb. That should be the current through the capacitor. Select a capacitor which will consume a current of 0.5 amperes only. And you shouldn't allow any current more than 0.5 ampere. If the current is more than 0.5 ampere, voltage drop across this will be more, bulb will be gone, damar. So using this as current, solve these equations because it's now very easy. See, only one formula. Irms is equal to Vrms divided by Z. In this Z, capacitor comes into picture. So you can find it out. That implies, what is the, okay, here only I can write Irms is equal to Vrms divided by root of R square plus XCC square. But what is R? R is the resistance of the bulb. That we haven't found out. What is R is equal to? So we can do it like this. V is equal to IR. Same formula. V is equal to IR. For bulb it is okay. Or power is equal to V square by R. That is also possible. V is 100. I is 0.5 into R. So what is R? R is 100 by 0.5. 0.5 is 1 by 2. So R is 200 ohm. This is R. Now IRMS is equal to, okay, we will find out XC first, then we will explore XC, then we will get what is C. Hope you have followed now. Now only mathematical calculations. IRMS equal to VRMS, so by Z. IRMS we have got, this is the maximum current, that should be the circuit current, right? The circuit current itself should be 0.5 because bulb can tolerate only up to 0.5. That means that should be the circuit current. So 0.5, I have selected this itself as the circuit current. VRMS is this one, total voltage that is applied divided by, this is for circuit, okay, this is for bulb, this is for circuit, whole circuit now. VRMS divided by root of R square 200 square plus XC square, let it be XC square only, okay. So this 0.5 when it comes here it becomes 440, this is half, right, to 440, that implies root of 200 square plus XC square is equal to 440. Square it, when you square it what you will get? That implies 200 square plus XC square is equal to 440 square, okay. What else you have? Yeah, you have to get this one now. XC square is equal to 440 square minus 200 square, that is equal to 440 into 440, or you can do this one, A plus B into A minus B, right? Shall we do that? A square minus B square is equal to A plus B into A minus B, that is 440 plus 200, so A plus B into A minus B is equal to A square minus B square. 440 plus 200, 640, 440 minus 200, 240, isn't it? 440 plus 200, that is 640, 440 minus 200, 240. Yes, that is 640 into 240, that is 15,003, okay, that is, okay, 15, so 1,53,600, 1,53,600, that is XC square. What is XC? That implies XC is equal to square root, where is square root? Yes, 391.9 ohm, 391.9 ohm, that is XC. But they are asking you capacitance. What is the capacitance of the capacitor required? Capacitance of the capacitor required, you have to expand it again. Yes, I'll do it here. XC is equal to 1 by 2 pi nu C. XC is 391.9. 391.9 is equal to 1 by 2 pi nu. Is it 50 hertz? Yes, 50 hertz. So shall I write it as 314 C? What is C equal to? C is equal to 1 by 391.9 into 314, because 2 pi nu is 2 into 3.14 into 50. Okay, C is equal to 1 divided by 391.9 is equal to divided by 314 is equal to 0.000. Shall I write the answer here? 0.00. How many zeros? 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Then 8. 1, 2, 6, 3, 4. 1, 2, 6. That is equal to 1, 2, 3, 4, 5, 6. 0.8, right? 0.8 micro. What is the answer? I don't find the answer. 1.26. 126 microfarad. No. Is it 8? So I think it is hidden here, 8.126 microfarad. It is 1, 2, 3, 4, 5, 6, 0.8126 microfarad. This is the capacitance of the capacitor to be put. This formula is it should come down, so that's a problem here, and that has to come down. 0.8126 microfarad, and okay, that is the capacitance of the capacitance to be connected, so that you can safeguard the bulb by not crossing 100 volt or not crossing 0.5 amperes. This capacitor will do this. Now the next question is, does the lamp continue to glow if the capacitance of the capacitor is double? If the capacitance of the capacitor is double, does the lamp continue to glow? No, because what happens? You know, Xc is equal to 1 by 2 pi nu c. What happens then? When Xc, when C is doubled, C is increased. When capacitance is double, Xc decreases. If Xc decreases, what happens? Total impedance decreases. That equal to root of R square plus Xc minus root of R square plus Xc square, right? So Z is equal to root of R square plus Xc square. So when Xc decreases, Z decreases. I'll write it here only. R square plus Xc square. So when free capacitance is double, Xc decreases, Z decreases. If Z decreases, current increases. When current increases, it has to operate only under 0.5 amperes. Then bulb gets damaged. No. So bulb, does the lamp continue to glow? No, it will get burnt. So it won't continue to glow. Let me check it once whether this 0.8126 is correct or not. I will simply check it here, because that formula has come all the way. It has to come down actually. Yes, we have the answer there. Yes, yes, it is correct. 8.126 microfarad they have written. 8.126 microfarad. That I have to check now. Is it 8? 1, 2, 3. Ah, yeah, right. You can check it. You will get this. It is not 6 zeros. 5 0. 1, 2, 3, 4, 5. Sixth place is 8. Only this much. Right, 1, 2, 3, 4, 5, 6, 8.126 microfarad. Yes, that is the answer. So that is about the 9th problem. From 10th onwards, we will go to the next video and we will continue it. Thanks for watching my class. We will continue the problems. You can work out the problems yourself, and if you have time. Thank you.